Anyway, so this work is something that actually builds on a slightly older work, mostly done by Stefan and some other people, which introduces this idea of echo verification, which is an error mitigation technique for mitigating error occurring in noisy calculations. But in this work, we extend these ideas to also mitigate non-adiabaticity occurring from finite time quasi-adiabatic evolutions. So I'll take you through how we did this and how it works. So in this talk, I will first introduce error mitigation by echo verification. Echo verification as an error mitigation technique. Show how we translate it to the adiabatic computing setting. I will go over the main technique that we use in the extension to adiabatic computing, which is the phasing channel. I will explain everything about this, and then give a summary and outlook for future work. So error mitigation by echo verification is interesting because, well, as you know, any device for state preparation, be it analog or digitized, will produce some kind of noise. And while error correction is far away, we have to resort to some kind of error mitigation method. And there's a bunch of these methods, like noise extrapolation or device-specific calibration, a bunch of things. One class that we're focusing on here is the class of purification methods. And the idea is that if you have a noisy version of some ideal state that you want to measure with respect to which you want to measure the expectation value of some observable, then you can reduce the bias in this estimation by effectively raising this noisy state to a higher power. Why does this work? Because as you increase the power to which this noisy state is raised, you will find something that is closer and closer to the dominant eigenfactor of this noisy state. And in particular, if the noise is orthogonal to the ideal state that you're looking for, then you can just basically do a basic calculation and find that the error in estimating your expectation value will scale as over epsilon to the k, where epsilon is the error rate in your noisy state. So, of course, this is a specific case, but in the setting that we consider, where also we take k is 2, we will engineer a situation where we can get obtain a state that is epsilon close to a state where the noise is orthogonal to the ideal state. Okay? So echo verification, that's what this is all based on, is a method that achieves this purification to degree k is 2. And we're restricting ourselves to unitary operations because, we're implementing this operation of this operator as a control gate. But if you want to extend this to any Hermitian operator, you can basically decompose it as a weighted sum of unitaries and still apply this technique. So the idea is to implement the circuit here. It's pretty similar to an Adamar test circuit, except, we provide some noise as well, and crucially there's a measurement on the system register at the end. So not just on the auxiliary qubit, but also on the system register. And this measurement is what we call a verification measurement, and what it does, it projects on the initial state. So if after preparation and unpreparation at the end of the circuit, we get the same state back as at the beginning, we say the measurement or the protocol is verified, and we take the outcome of the measurement on the auxiliary qubit as a contribution to our total estimate of the expectation value. Now what this does, you can also write this out, is it measures an sample with an expectation value that is the real value of the trace of your observable with this noisy state squared. Okay, so this is where we're raising the noisy state to the second power. If you replace the x up there with the y gate, you get the imaginary parts, and if you entirely get rid of the operator, you get the normalization factor, so you combine the two and obtain the expectation value for the squared operator that is normalized and which we're using as our estimate. So how does this relate to adiabatic computing? As we all know, let's say we want to progress to ground state, then a noiseless quasi-adiabatic sweep will produce a state that is, well, not exactly the growth set that we're looking for, but it has some error which depends on the total time that we're sweeping with and the minimum gap along the path. And this means that if you take this state as a reference for measuring your expectation value, then you will get an error that's if the error in the adiabatic state is epsilon, then the error in your expectation value will scale as order square of epsilon, or as order of epsilon if the operator has no couplings between the ground state and any orthogonal state. With error verification, we will improve this to epsilon squared. Okay? So these would look like this, and well, as you can probably guess, at this point we assume that the adiabatic superpressure is noiseless, so the state that's prepared here is a pure state, and well, therefore squaring a pure state doesn't do anything, so this is not going to do us any good. However, what we can do is introduce some artificial noise, which will promote the coherent error that makes the adiabatic state deviate from the true state that we're looking for to an incoherent error, which we then can mitigate using this echo verification circuit as explained before. This artificial noise channel that we're introducing is called the dephasing channel, and I will talk a bit more about that in a bit. However, I first want to mention something, namely that implementing this unpreparation gate at the end of the circuit may be, well, non-trivial or impractical on hardwares, especially since I was in the beginning kind of focusing on this near-term hardware, especially if you're thinking about analog simulators, then this will be, well, this will be not straightforward because you would have to invert time or invert the energy spectrum or do something weird. So what we do instead is replace this unpreparation gate by a reverse adiabatic sweep, or we just invert the schedule. And we expect that this acts approximately the same as an unpreparation gate because, well, at least in the infinite time limit, they're the same up to a phase, but still they should connect the initial ground state and the final ground state in a somewhat similar way. And, well, if not, I guess the epsilon delay they used in the beginning, you can just take it to be the maximum error, either produced by the forward or the backwards gate. So, onto this dephasing channel that I promised. As I said, the idea is to bring the noisy state into a form where the error is orthogonal to the state that we're looking for. Okay? And this is possible by dephasing the noisy state, the adiabatic state. Sorry, I said we're trying to bring the adiabatic state into this form. Okay. And this is possible by dephasing the adiabatic state in the eigenbasis of H. And what this does is, well, it just kills off the off-diagonal entries in the Hamiltonian basis. Okay? However, we cannot do this exactly, right? Because, well, we're looking for a ground state of the Hamiltonian in the first place, so how can we even know this dephasing operation exactly? However, what we can do is an approximate version of this dephasing channel. And the idea is to time evolve the adiabatic state with respect to the Hamiltonian and some random time that is drawn from a compactly supported probability distribution, because the resulting channel will look like this. And what it does is that if you look at the matrix elements of this row here in the eigenbasis of the Hamiltonian, then it will basically multiply every element with some Fourier coefficient that depends on the energy difference between levels, the difference between all of the energy levels. And we note here that the diagonal Fourier coefficients will be 1, because you're just integrating over probability distribution. And a crucial observation here is that as long as the probability distribution over your dephasing time is smooth, then these Fourier coefficients, or at least the magnitude, will decay with the dephasing time, and also with the respective caps. So we have something that we can use to, in the asymptotic regime, in the asymptotic limit of infinite dephasing time, kill the off-diagonal elements that we don't want. However, since in the beginning I mentioned that we are only looking to improve the error to epsilon squared, it suffices to actually only kill off these off-diagonal elements approximately. And so, the bottleneck here is, or actually really the crucial, the important figure that we're looking for here is this Fourier coefficient between the ground state and the first excited state, is F01, because all the gaps between the ground state and any higher lying excited state will always be bigger than, well, the gap between the ground state and the first excited state, meaning that this F01 coefficient will remain the largest, and therefore we'll have to put the most effort into killing off that specific element. And well, one of the results in our paper is that the estimation error in measuring an observable after this whole dephasing, or this whole protocol of using this echo verification in combination with the dephasing channel will be for world scale as something of the order of square epsilon times this F01 coefficient plus something that's already epsilon squared. Okay? So we would have to find a Fourier coefficient that scales as epsilon to the 3/2 to make all errors epsilon squared. Now, of course, the question is then, what probability distribution should we choose? And this will determine also the relationship on the dependence on the dephasing time that we do. So we want, of course, the Fourier transform of this probability distribution to decay fast with the dephasing time, and well, as a result, also with the relative gap. And a function or probability distribution that has this property is this bump function. It's an interesting function. It's actually compactly supported on this interval between 0 and the dephasing time, but nonetheless everywhere differentiable. And there's something that's called the Gibbs phenomenon that will tell you that if you have a function that is infinitely differentiable, then its Fourier transform will decay superpolynomially. And this is, well, okay, something we actually observe. You see that the Fourier transform decays as e to the power minus square root of the dephasing time times this gap, okay, divided by 2, sure. And that means that the dephasing time that we need to sufficiently kill off these off-diagonal elements actually grows very slowly in the error that we have, so the inverse error that we have in our adiabatic or quasi-adiabatic state. And also, I want to emphasize that the dephasing time here depends on the ground state gap only at the end of the adiabatic protocol, and not on the ground state gap, not on the minimal ground state gap along the path. And well, there are settings where these things are the same, but there are also settings where these could vastly differ. So that's another merit of this strategy. This is a little numerical example, experiment that we did to, well, verify this algorithm. And as you can see, there's the standard quantum adiabatic algorithm depicted with a solid line. If we picked dephasing time to be 0, well, you could just get a double sweep time, so it doesn't do anything. But as we increase the dephasing time, you'll see that the error is actually decreasing quadratically in the asymptotic regime. And sorry, I forgot to mention what the observable is here. The observable here that we're measuring is a reflection about the ground state, which means that it also doesn't have any couplings between the ground state and any excited states, so therefore we see only a quadratic improvement and not a quartic improvement from square root to epsilon 2 squared, to epsilon squared. Okay? So, summary and outlook. We have introduced this adiabatic echo verification protocol for mitigating non-adiabaticity in, well, adiabatic quantum computing. And it implements this circuit which does a forward adiabatic sweep, then introduces this artificial noise, which we call dephasing, controls version of the operator that we want to measure, another dephasing round, a backward sweep, and then a clarification measurement at the end. So what it does is it improves the bias in estimating an observable with respect to the true ground state from either square of epsilon to or epsilon to epsilon squared. And this is done. This works because the dephasing channel promotes the coherent error from adiabatic state preparation to an incoherent error in such a way that we obtain something that's or epsilon squared close to a state that has orthogonal error to an error that's orthogonal to the ground state. And then the echo verification protocol effectively squares this state, which also squares the error. And that's where the error improving performance comes from. It has a number of benefits, namely that the time overhead which we get from implementing this protocol is small, namely it grows very slowly in the error, and also, well, as I mentioned, it grows in the final state gap, in the inverse of the final ground state gap and not the minimum ground state gap. And, well, I said that the polylogarithmic scaling in this epsilon follows from a choice of the probability distribution, which is infinitely differentiable on this whole interval. Okay, yeah, this I already mentioned. And it's also made friendly to noisy hardware because, well, we choose to explicitly implement backward sweep instead of a number regression gate. And also, I'd like to emphasize that since this protocol was in the beginning already meant as a way to mitigate noisy errors from noising gates, this should also carry over to the adiabatic context. So for future work, we're considering to look into a few things. Namely, of course, this introduction of the dephasing channel will alter the sampling costs that you need to make an accurate measurement. I'm not exactly sure at the moment what the dependence would be, but I think it would grow in the order, in the error itself. But this is under investigation still. A second thing is that, of course, it would be more realistic to get rid of the controlled O operator in some way, because, well, if I'm talking about analog simulators, well, which analog simulator really has controlled operations? In the original echo verification work, there was also a proposal for getting rid of this controlled O operator. However, this requires a certain coherence with the reference state, which would be destroyed by the dephasing channel. So this doesn't work, but there might be other options to get this working. Lastly, I think it would be cool to combine this adiabatic echo verification protocol with other purification methods, such as virtual state distillation, which I think was also mentioned on one of the posters here, because, well, this virtual state distillation uses multiple copies of pairs of your state to to basically exponentiate your state even further to higher powers, and that would also allow to reduce the error further. But again, under investigation still. So with that, I would like to thank you on behalf of myself and my collaborators, and if you have any questions, please. Thank you.
Thank you for the talk, Dyon. So, we're open for questions. Okay, maybe let me start with a quick question. So, I have a question regarding your protocol. So, in your protocol, when you're computing the overhead, do you have to run twice the
so you have to run bitwise.
There is an inversion, right?
Yeah, so you have to go forward in your adiabatic evolution and also go backwards.
So you need a double round.
Yes, yes. But this is a constant, and if you just naively we try to improve your adiabatic error by doubling your evolution time, then this would lead to a constant decrease in your error as opposed to a quadratic improvement in your error.
I see.
Could you, I think you mentioned it, but could you reiterate how sensitive is this method to the fact that you actually don't have the exact inverse, but just run the schedule backwards?
So we don't have a very precise formulation of how sensitive this would be, except we expect it to be the reverse protocol to be somewhat similar to the imperfection gate, because the energy spectrum, of course, along the path will be the same as when you're evolving forward. So since the gaps here are they will be the same, the estimate, or at least the usual upper bound that one uses to estimate the fidelity at the end of the protocol will be the same in both directions. So that is the reason why we would assume that they should not be too far off.
Okay, thank you.
So you use the error mitigation method. So it means you assume like risk devices,
Yeah.
noisy device, I think. So your proposal assumes the quantum circuit is much longer. So if you have risk device, such a device is affected by the coherence. So if you consider the much longer quantum circuit, the decoherence may affect your proposal. So how about do you consider that?
So, I guess the question is what you mean by much longer, because, we only double the size of the circuit. And, for this I would actually like to go back to the original proposal for echo verification, which was initially invented as a means to exactly mitigate the noise from such NISC circuits. And this has also been experimentally verified that this works very well to mitigate errors in, basically circuits of the scale that we're currently able to operate. So, as such, I would expect that this adiabatic echo verification method would also work would have the bonus of also mitigating errors from decoherence in your NISC circuits.
Thanks.
Thanks for the question.
Okay, any other questions? If not, let's